So quick intro, and then I'll let you go through your slides. So Christopher Helpa from TTTech, one of member of the innovation team that is part of the city office, and essentially performing research in the context of automotive software. Your screen is showing, so you can share your slides. You can go on presentation mode. The floor is yours. Best of luck with the presentation.
All right, you see my slides, right?
Yes, I do.
All right, awesome. So thank you very much for the introduction. I'm really glad to be here and talk about Zenoh Flow, another exciting technology from ZettaScale, and also how we are currently working with ZettaScale to add additional features, which we think are very critical for autonomous driving applications in general. So before we jump in, let me briefly explain you what we are focusing on. So autonomous driving is a huge domain, and as a company, we focus on safety aspects. So what does this mean, right? I mean, safety is the domain of ensuring that the system is working in a way that no one gets harmed. And there are multiple things to do this. First of all, when you develop your application, you need to ensure that you're building the right thing. So when you're building an autonomous driving application, you need to design it in a way that it works in all driving scenarios, that it works in all environmental scenarios, that it detects all the obstacles it needs to. So this is basically making sure that you're building the right thing. This is something we are not focusing on. So as a company, we are a platform provider, but we are providing a platform so that autonomous driving applications can be hosted. The second thing in safety is ensuring that you're implementing it right. You need to show that you are sufficiently free of design faults, right? So this has two aspects of it. First of all, the function must work correctly. You must show that what you have implemented just works and does what it is supposed to do. But the second thing, and this is one thing that we focus on mostly, is it needs to fulfill timing requirements, right? So an autonomous driving application interacts with the environment. It needs to react to things, and it needs to do this in a bounded amount of time. Otherwise, the output it produces, like steering or evading objects, is useless or even harmful. And in general, it is not possible to prevent all faults and all bugs. I mean, software development is complex. It is not possible to write bug-free code. So you need a second layer of defense. So you need to monitor the system and react accordingly if something goes wrong. And lastly, you must show that all of this is working as intended. So you need to validate it. You need to argue that the system is correct. So in our domain, for software development, this means you need to follow some safety standards. And in our case, this is the ISO 26262. And this basically tells you need to have a proper safety design. You need a top-down waterfallish process to ensure that you are really building the right thing and you are building it the right way. And there they mandate some design patterns. You need to avoid error-prone solutions. So take simple solutions, proven ones, build a deterministic system. So really see that you get what you want, right? And you're not surprised by randomness, which also means you should prevent dynamic behavior as much as possible, because then you introduce possibilities for race conditions and things like that. And if you do this, you get some nice properties out of this. So first of all, you will have designed a system that is easy to analyze, to review, to argue that it is correct. It will be simple to test. If it's a deterministic system, the tests will be reproducible. You don't have too many complex testing scenarios, and they have a high quality, and they can show that it is working as intended. And all of this you can then put into some safety argumentation. So basically you propose a way, so you explain to someone. It's a bit more complicated than that, but you can imagine it like this. You pull together all of your evidences, what you did, and argue that the system is safe, and this should be easy to understand. You cannot have very complex arguments that no one can follow, so this should be simple to do. So what do we do as a company? So we are a software platform provider. We have like two main products. One is MotionWise, which is based on adaptive AutoSAR, which is a whole platform which provides certain properties to the system. So it is predictable, it is real-time capable in the sense that we provide real-time capable scheduling mechanisms. It's scalable and things like that. And it provides features like state management, health management, safety supervision, as well as communication and time synchronization. The other one that we are working together with ZettaScale is Zetta Auto, which is a safety certified DDS stack. So again, we're not doing application development itself, but we provide basically everything that an application developer needs to implement and integrate their applications into the system. But we need to follow certain architectural patterns. We're not free to design this in a proprietary way. The automotive industry settled a few years ago on providing a standard for software architecture and the whole ecosystem. The goals for this are clear. You want to have interoperability. You want to, as an OEM, be able to easily integrate applications from different suppliers. You want to be able to exchange suppliers. You want to be as agnostic from proprietary things. And for the software suppliers, of course, it's helpful to implement the standard because it will fit into any OEM. Historically, this comes more from the control things. So there was before classic AutoSAR, which is really focused on embedded hardware. So really focused on control algorithms and things like that. This changed a bit with adaptive AutoSAR. It's more focused on general application development, but it still inherits a very, it's an approach that is very heavy on configuration. So the main problem was always how to configure the overall vehicle, how to integrate applications which are quite simple, but you have a whole car to configure. So you want to handle how to deploy them, how to configure them. And this workflow was carried over to some extent. So there's lots of configuration aspects. You need to define your applications. You need to define services. You need to define interfaces. You must map them together. You must design the specification of the machine. You need to deploy them. And all of this is following this idea of having everything offline, having everything as human readable things, and very little code. So software development in this flow is only this small box up there. It's all about configuration. It's about generating things. This is good for the integrators and the safety engineers because they do not need to read code to argue about what is going on. But for developers, this is not so ideal because whenever something needs to be changed, a new interface added, a deployment changed from one host to another, they need to go to this world they don't really know too much. You need maybe to go to the integrator to change things. So software development is relatively slow. And for autonomous driving, this is a bit of a problem. So one salvation, or is it a salvation, would be to go more to developer-focused things, like, for example, ROS2, right? There, it's awesome. It works well. You can easily build something. You can get something up and running pretty fast. It's easy to configure. Not much configuration needs. Not a lot of tools. Everything is code and everything is dynamic and it just works. So developers love this because they can get their application up and running fast. But integrators and safety engineers are not so happy about this because they might not be developers. They're not focused on being able to read code. Finding this information that is critical is hidden somewhere. So that's not so good for them. And lastly, so from configuration, all of this is fine. And lastly, one of the aspects I already mentioned is from functionality perspective, we need to ensure that we produce outputs in a given amount of time. So there's always this model of autonomous driving where you sense something, then you do sensor processing, fusion, path planning, control, and then actuation in kind of this kind of this chain, right? And what you now need to argue is that this happens in a bounded amount of time. So fast enough before you crash into the overall system. But the problem is that this is kind of a model that does not really hold. In reality, this processing chain is a complex graph of lots of interacting components. So what do we now want, and why is Zenoh Flow interesting here? So first of all, we need a mix between this flexibility that developers really want and this offline analyzability to make the integrators and the safety engineers happy. It needs to be balanced somehow. It's not A or B, because you're just shifting like the niceness from one persona to the other. We need to find a balance. We need predictable end-to-end latencies of this overall processing. We need a very deterministic execution. In our case here, we're going for data flow determinism, and we need to control when something is not working as intended, right? Dealing with temporal aspects where also scheduling is involved is always hard, because software developers are not used to this, right? When you develop software, mostly you're taught you have as much hardware as you need. It just runs, and as long as it's not lagging, it's fine. That does not work for real-time systems. We need to really focus on getting the timing right, but this is not always possible, and therefore we need to control the system in a way that is still safe if something does not match what we expected. So Zenoh Flow provides a data flow programming framework. So what does this mean? When you design your application, you model it in a directed graph where we have flow of data between operators. So you can see this like this. You have this source operator that provides some data, which is then operated on by this operator B. He passes it on to C and so on. So the data flows through the system in a way that it triggers the computation, new outputs are produced, and then it goes on. So Zenoh Flow allows to express this explicitly, and you already see, if you compare this to before, where we had this complex processing graph, this looks quite similar. So how is this done in Zenoh Flow, and why is this a nice approach that could balance this offline configurability and the flexibility? In Zenoh Flow, you describe your data flows. So you describe the nodes that are involved, your processing elements, the data names that are exchanged, and the links between them. So if you take this example here, so you define your camera. Your camera is your source node. It produces some output, and then there's another operator that does something. In this case, it's a facial recognition one that has some inputs and some outputs, and then you can link them together. So you say, okay, camera produces the output stream. This is mapped to the node facial recognition, which considers this his input, and with this you define the overall flow through the system. So this is nice because this is a human readable format, but it specifies the whole processing. So you can analyze this offline. You do not just need to run it and then produce something like an architecture graph in ROS2 where it tells you how the system interacts, but you get this upfront and you can analyze this upfront, whether this makes sense or not, and the system will just behave exactly like that. And finally, you have a mapping of where the nodes run. So you map your nodes to some compute elements. And this allows us now some extensions that we are currently working on with ZettaScale to add. The first thing is you can now take this graph and control the execution through the graph. So you take this input definition, you build up your whole graph, and then you know if a certain node finished, which ones are the ones that should execute next. So if you see here the first one finished, you know that 2, 3, and 4 could be executed because they only depend on data that is produced by the first node. If you then go on and say, okay, you have finished the node 4, you can look again at the graph, but then you see that you cannot yet dispatch this node 8 because node 8 also depends on the inputs from 7 and 3, but it did not run yet. If this had been a purely data-driven system, like in ROS, for example, operator 4 would just produce the data, which would cause an interrupt at node 8. It would run, do something with the data, figure out it should not run yet, and go to sleep. So it would be woken up each time new data arrives, which leads to overhead, indeterministic behavior, race conditions, and things like that. And you need to handle this as an application developer. In Zenoh Flow, if we have the guided execution, we will only dispatch it once all of the data is actually here. And now we can add scheduling and real-time behavior to it. So we have this graph, and if we annotate our nodes with timing requirements, time and budgets, or timing contracts, if you want, we can analyze what the overall temporal behavior of the system will be, and you can control the dispatching in a way to optimize the system. So just briefly here, those two examples. If this first node is finished, and we now know that 3 nodes could execute, but we only have 2 cores, then we need to make a decision on which of those 2 nodes we want to execute. If you don't control this, then this will just happen due to race condition. Whoever is triggered first by the scheduler will run first, but thanks to Zenoh Flow, we can do better. And we already see, I'm not going through the whole trace, but just to illustrate the point, if we dispatch nodes 2 and 3 first, we will get an overall latency of 40 milliseconds. However, if we decide to dispatch 3 and 4, we will get only 50. Why? Because in the second step, the only node that could be executed is this node 2, because nothing else is ready. And therefore, we are not utilizing the CPU efficiently because one core will go idle, and therefore the overall execution time will be longer. So we have all this timing information available, these timing contracts. We know the graph, so we can introduce data flow scheduling into this. So we can really analyze the graph offline, take this timing, run some heuristics. Scheduling is NP complete, so we can never find an optimal schedule, but we can run some heuristics that optimize the critical path. So we can, thanks to the data flow graph, basically see into the future. Whenever we dispatch a node, or when it finishes, we invoke the scheduler, and it can look at what has already executed, what we need to execute next, and which will be the best node to execute in order to have the lowest overall latency. So we do this at runtime whenever a node finishes. So this means also that we can tolerate that nodes don't always use up all of this time. So it might just finish. If this were a fully offline generated schedule, we could not do this, but we do this dynamically at runtime to take this into account. And last but not least, we said that we need to control when something goes wrong. So those nodes have those timing contracts to say, okay, normally I should just finish in 10 milliseconds, and the system is designed for exactly this. However, it could of course happen that it runs longer for whatever reason. If this happens, we would not be time deterministic because the whole processing is delayed. It takes longer than we thought it would. But you might want this during early development when you want to test things and see whether the functionality is up. That's fine because it's data and data flow deterministic. We always get exactly the same. But when it's running in the real system, you might not want this. You want that it reacts in 40 milliseconds. It's acceptable that the output is not ideal, right? So you can tolerate some data loss. So what we would do is, if the node violates his timing contract, we stop it. But for the overall processing, we just go on. Meaning, if eventually those nodes 7 and 4 finish, we will still dispatch node 8. This means that he will not get the data that 3 produces. It needs to be able to deal with this. And the output will not be exactly the same as normal, but you're still guaranteeing that you're producing an output in this 40 milliseconds, which means you're still evading an obstacle you might have detected. It might not be the ideal maneuver, but you're still going to be safe, and this is what we're striving to do. We're also working currently, ZettaScale mostly, on how to add prioritization for mixed criticality, that you can have multiple of those graphs at different priorities, core pinning, and other things to optimize the system further. So to sum it up, From our perspective, as I said, we need a system that balances the needs of both the integrators and the software developers. We cannot do all of this complex offline configuration because it slows down developers, but we cannot do nothing, right? We need a balance of this, and Zenoh Flow provides this thanks to the overall architecture configuration that it adheres to at runtime. So this looks like it provides a very good balance of those aspects. It allows us the data flow deterministic execution, and with the scheduling, we can optimize the overall end-to-end latency, which provides you additional performance benefits, and we control when something does not conform to this contract you have to ensure that the overall execution maintains safe and we fulfill our real-time requirements. So this is it. So thanks for your attention. If there are any questions, I'm happy to take them.
Thank you very much, Christopher. Questions will be asked, are being asked on social media. So please keep an eye on LinkedIn, Twitter, or YouTube. That's where the comments and the questions are going on. Thanks again for taking the time and sharing, your experience with Zenoh Flow. Let's thank, obviously. And
thank you for having me.
Yeah, our pleasure. So Luca is next on what's next, right?
Exactly.
Okay. Thank you again.